Moving on from our discussion of gases, we're now ready to talk about solids and liquids. The large difference between solids and liquids is that the particles are not close enough together and moving slow enough that attractive forces become incredibly important in determining the properties of solids and liquids. So we're going to go through a number of things in that realm. We have to look very deeply at those types of forces that are holding them together. So we'll take a quick look at the states of matter, compare inter and intramolecular forces, we'll look at properties of liquids, phase changes, vapor pressure, phase diagrams, and then briefly talk a little bit about the structure of solids and some bonding in solids. Review of the states of matter. So gases will have both the shape and volume of the container. They're compressible, they flow easily, and they will diffuse within fairly rapidly. Liquids assume the shape of the container but not the volume. They do not expand to fill the container, in other words. They're virtually incompressible. They flow readily, and they will diffuse within a liquid rather slowly. Solids have their own definite shape and volume. They are, again, incompressible, similar to liquids. They do not flow, and diffusion through a solid occurs even more slowly than liquids and definitely slower than gases. If we look at things on the molecular level, to try and understand those things, obviously in a gaseous state, particles are moving freely throughout the container, and they can, there's again no attractive or repulsive forces there. If we cool a gas down, we change into a liquid, so now the particles are coming closer together because of the attractive forces. The energy isn't high enough to overcome those attractive forces, so the particles will condense down. They're free to move within the liquid, but again, they will not expand to fill the container. If we cool the liquid further, the attractive forces become even stronger and you form a crystalline solid. And in most cases, you get an ordered arrangement of those particles in which they're fixed in position. And of course, heating would take things in the opposite direction. First, we want to make sure that we have a very clear idea of the difference between intermolecular and intramolecular forces. Now, this discussion doesn't happen with ionic substances for the simple reason that they do not form molecules. So ionic substances only have one type of attraction. Those are the ionic bonds that hold the ions together. In covalent substances, or molecular substances, there's two types of attractions. One is the covalent bond, which is a very strong attraction, and the second is an intermolecular attraction, which is much weaker than that covalent bond. So if we had a sample of hydrogen chloride and it was in, say, the liquid state, if we were to heat it, we could change it to the gaseous state. In that process, we would be weakening and eventually breaking that intermolecular attraction here, as that would be the easier one to break apart. The covalent bond, the intramolecular, would not break apart. Most of the discussion in this chapter will center around those intermolecular attractions. The general form we give for all those intermolecular forces is the term van der Waals forces. So all the forces we talk about will be lumped under that broad category. The types of properties that are influenced by intermolecular forces, well, there'll be a variety that we'll talk about. You're going to want to kind of generate your own list, but just to give you some ideas, obviously the boiling point would be one. The temperature at which things separate from the liquid and go to the gaseous state. The stronger the attraction forces would be, the higher that would be. Viscosity is one that we'll look at for liquids. This is the ability of the liquid to flow. The enthalpy of vaporization. delta H vape. Okay, so the energy it takes to vaporize something, obviously if there's stronger attraction, it's going to take more energy to vaporize things. So there's some other things too that we'll talk about in this chapter. So keep your eyes peeled for other properties that are influenced by these intermolecular forces. Of course, we want to make a list of those types of intermolecular forces. The weakest of all of them, and this is somewhat of a general term, as these intermolecular forces are going to depend on different factors. But in general, the weakest type are things called London forces, or London dispersion forces. Okay, so they tend to be the weakest of these. Then we have dipole-dipole forces. Okay, so they tend to be stronger. How do we determine the difference between these two? Well, dipole-dipole forces are going to occur between molecules that are polar. So remember back when we did the molecular geometry and we looked at whether molecules were symmetrical or not, and if there was a net pull of electrons toward one side of the molecule, creating a polar molecule. That polar molecule then would have dipole-dipole attractive forces. If the molecule were nonpolar, then it would only have London dispersion forces. Now it's important to note that all substances have London dispersion forces. So it's not just nonpolar substances, but it's all of them. Again, the difference is that nonpolar substances, that's the only type that they have, whereas polar molecules would also have dipole-dipole forces. And then we'll also talk a little bit about a special or a very strong type of dipole-dipole attraction called hydrogen bonding. And we always want to be careful with that hydrogen bonding because of the word bonding in there. We tend to think of bonding as ionic bonding or covalent bonding. Hydrogen bonding, although it's strong, is still not nearly as strong as a covalent, an intramolecular covalent bond or an ionic bond. These are all intermolecular forces that we've discussed prior, in prior years, first year chemistry. What we do want to do is branch out a little bit and include attractions between different types of particles. So we've seen these already. When you dissolve things in water, you see water molecules, as in the picture here, the polar molecules with ions. These are ion dipole attractions, both with cations and anions. We want to kind of expand our thinking about these to include those type of attractions as well. So here we have a kind of a set of ion or dipoles, polar molecules, and again, kind of expanding on our thinking about this. We don't just think about, ordinarily we would think, all right, well, we've got a positive and negative end, and I take another molecule on the positive and negative end, and we would have an attraction that exists between the positive and negative ends, and so that would be our dipole-dipole attraction. Well, we also want to think about all the repulsions that are happening. So if you look over in the picture on the left here, all of the red lines represent attractions, where you have parts of the molecules that are attracting to other parts of other molecules. The blue lines are repulsions, and so you have to remember those exist as well, and so there's a balance between that. Down at the bottom we see a table that shows us the relationship between the dipole moment of the molecule, which again is the sum of all of the the bond dipoles to create that dipole moment for the molecule. But if you look down the list, they all have a very similar molecular weight. And so we're keeping that constant, but we're looking at the dipole moment, and as that goes up, you can see that the boiling point goes up as well. So obviously the greater the dipole moment, the more the electrons are pulled toward one side of the molecule, the stronger the dipole-dipole attractions and the higher the boiling point would be. If we take a look at just a single helium atom, we see that there's for this one atom, the electrons would tend to move to opposite sides of the atom, so you wouldn't have a polar molecule. However, if at any particular instant we had one atom where the electrons happened to be on one side of it, if there's another atom next to it, or this could be just a nonpolar molecule, the electrons, because this side of the molecule then would become more positive and this side negative, what you would tend to do is pull electrons from the atom that's next to it closer to there. And what you create is an induced dipole. And this will form a temporary dipole moment, which would then allow this molecule, or this atom in this case, to attract together with other ones. So if I bring this up here, and take a look at it. And so this would be that attraction that's due to induced dipole. This is the nature of the London dispersion forces. With those electrons constantly moving around, there's a chance that they can move to one side of the molecule, induce a dipole in the molecule next to it, or the nonpolar molecule or the atom next to it, and create that momentary or instantaneous attraction. Again, it's very weak, especially for very small molecules. However, we can get rather strong attractions with these London dispersion forces. Now, the amount to which, or the degree to which electrons can shift to one side of the molecule and form this dipole is referred to as the polarizability. So the more polarizable the molecule is, the more likely it is that you'll have stronger attractions. So the factors that would affect this polarizability or strength of the London dispersion forces, there are two of them. The size, so larger makes it more polarizable. And the shape, so with the shape, let's see, the more spread out, or the more linear, the molecule makes it more polarizable. And we'll see some examples of this in just a minute. All right, so first with the size, if we take either our halogens over here on the left or our noble gases over on the right, our halogens going down, fluorine, chlorine, bromine, iodine, slowly getting larger in molecular weight, and you can see that as you go down, the boiling point also gets larger. So the larger the molecular mass of a nonpolar molecule, the stronger the London forces and the higher the boiling point. Get the same kind of trend with the noble gases, xenon being the largest molecular weight and having the largest boiling point. Okay? So that size, or the mass of the molecule, plays a role in how strong the London forces are. With shape, here we have three different isomers of pentene. And you can see that in the N-pentene at the top, you've got a boiling point of 309.4 Kelvin. Not sure if you can read that. That's for the boiling point. And the neopentane, in which you've got the carbon atom with the other four carbon atoms surrounding it, right? So rather than a straight chain, they're all together there, and the boiling point there is 282.7 degrees Kelvin. So not a huge difference, but very much a difference. So the neopentane, the one at the bottom, because the carbon atoms are bunched together, you don't get nearly that movement of the electrons or dispersion. With the N-pentane up at the top, there's much more surface area for contact, for interaction, for those electrons to get distributed to one side of the molecule and create stronger London dispersion forces. So the one question that always comes up is, which will have a greater effect, dipole-dipole interactions or London dispersion forces? Well, it's going to depend. If you have two molecules that are comparable size and shape, dipole-dipole interactions likely will dominate the force. If one of the molecules is much larger than the other, then the dispersion force is likely to dominate its physical properties. Water and candle wax is a great example. Candle wax is nonpolar. It's a hydrocarbon, so it's a nonpolar molecule, and yet it exists as a solid at room temperature, as water, which has hydrogen bonding, exists as a liquid at room temperature. And here's a graph that we've seen before demonstrating that hydrogen bonding, where we have this normal trend of mass gets bigger, boiling point goes up. Mass gets bigger, boiling point goes up, except for water. And the reason for that is the hydrogen bonding that occurs. And we'll recall this is going to happen anytime you have hydrogen bonded to either oxygen, hydrogen bonded to fluorine, or hydrogen bonded to nitrogen. All right, in all of these cases, you're going to be pulling most of the electron density away from the hydrogen, leaving just a single proton out there, which then creates a much stronger type of dipole-dipole attraction that we call hydrogen bonding. So here are some examples of this. So in the first one, we have just two water molecules together. Two ammonia molecules together here, but we can see that this does happen between different molecules as well. So anytime you have that hydrogen to oxygen and then the nitrogen bonded to other hydrogens, you can create those hydrogen bonds. And then we get different degrees of this in some organic molecules. So the hydrogen bonding is one we'll look at pretty carefully. And obviously in water, if we look at the crystal of water, we can see here that here's that covalent bond, and I shouldn't write over the distance there, but that covalent bond here is 1 angstrom, whereas the hydrogen bond, the attractive force between the two different molecules, is actually 1.8 angstroms. So it's not even it's not even close to the distance. It's almost twice as long from one water molecule to another in comparison to the bonding. So you can see that hydrogen bonding really isn't nearly as strong as the covalent bond. Okay, finally, this is just a table from your book, and you can kind of sort through this yourself, but it's a way to kind of use a flow chart, yes, no type thing, to figure out what type of attractions you're looking at when examining a different species. And I'll give you some examples. So it'd be worthwhile to spend a little bit of time going through this chart and kind of picking it apart to see how it explains the different types of intermolecular forces as well as intramolecular forces.